Hello, it's Mr. Colati here. Today we're going to be going through section 5.3, the section on mechanical energy. Mechanical energy refers to the two types of energy and the formulas we use to find them. Kinetic energy, which is energy from something that is moving, and gravitational potential energy, which is something that is raised to a height above a reference. Let's start with kinetic energy. Here's our formula here, and you can fill out the details from the slides. The first example, calculate the kinetic energy of a 72 kilogram cheetah running at its top speed of 33 meters per second. Wow, cheetahs. They're the fastest land animal, so we should be respectful of them. Look how fast they can travel to, 33 meters per second. And we want to find the kinetic energy, EK. So we're going to use our formula, EK is equal to mv squared over 2. I sub in my numbers, 72, 33 squared over 2. One little point, remember that mass is one of the only units where we use the kilo form. So we always use mass in kilograms. Everything else should be in its base unit. Okay, so I have 33. Be careful that you use the square button on your calculator. So 33 squared times 72 divided by 2. That gives me an answer of 39,204. Wow. And the units are, oh yeah, joules, because we're talking about energy. So that's how much joules, or how much energy, a moving cheetah has. Wow. Now, I know some of you might be upset about this. We should write it like this, 10 to the 4 joules. Okay, let's continue down the second example. The engine of an F-16 fighter jet. Wow, jets! Delivers 11.7 meganewtons of force. Wow, that's an odd unit we don't see very often when the fighter takes off from a runway of 63 meters long. If the mass of the jet is 8,570 kilograms and neglecting friction, calculate the work done by the engine. Oof, remember how to do work? Well, let's write out some numbers first. This 11.7 meganewtons. Well, newtons is a force. So that's going to be the force applied of my engine. I'm trying to find work, so I don't really care about direction, so I don't need to worry about the vector form of this. We know this is forwards. But I do need to figure out what mega is. Now, for those of you, if you forget, instead of going back to your notes, I'll teach you a quick way to remember. Think about a computer, right? A computer measures information in bytes. So you have 1 byte. If you have 1,000 bytes, that's 1 kilobyte. Now, if you have 1,000 kilobytes, you have 1 megabyte. So 1,000 KB is equal to 1 megabyte. So going from, for example, meters to kilometers, you multiply by 1,000. Going from kilometers to megameters, you multiply by 1,000. And similar here, 11.7 meganewtons is 1,000 times 1,000 newtons. So 11.7 times 10 to the 6 newtons. That's my kind of quick way of remembering this sort of thing. Always use my my computer lingo. The next one up, of course, after 1,000, when you have 1,000 megabytes, it's a gigabyte. 1,000 gigabytes, it's a terabyte, and after that, I don't know. Okay, now we know that runway. Okay, that has a distance of 61 meters. And the mass of the jet is 8,570 kilograms. Okay, so we want to find the work done by the engine, part 1. Well, work, I know the formula for that. That's F cos theta delta D. Oh, well, we know what F is. It's 11.7 times 10 to the 6. What about F or the theta? Well, I know that F is going forwards, and I know that theta, or delta D, sorry, is going forward. So therefore, I know that theta is 0 because these are in the same direction. And the displacement is 61. Okay, let me multiply all these things together. 11.7 to the power 6 times cos theta. Oops, messed up. 11.7 to the power 6 times cos theta times 61. And that, oh my goodness, it's a humongous number. That's going to be 7.137 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the 8 joules. Wow, that's a huge amount of work. Now, the final speed at takeoff. This is getting a little bit ahead of us. It's setting us up for our next lesson, which is on conservation of energy. But the work done by the engine is all given to the plane, and it's transferred to the plane to make the plane go fast. So the work given or done on the plane is turned into kinetic energy, and we're going to use the formula for kinetic energy to figure out what the max speed is. So I'm going to write out my value, my amount of energy, which is enormous. Then I have my mass, which is 8570. Then I have my v squared, which is the thing I'm trying to find, and I have to divide by 2. Okay, now let's just go through how to solve this. I want to get the v by itself. I want to solve for speed. So first I'm going to get rid of this 2 by multiplying both sides by 2. You don't always have to show this steps, but it is nice to go through one of these in detail. I end up with 1.4274 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9 is equal to 8570 v squared. Now, I want to get the v squared by itself, so I'm going to divide both sides by 8570. So I end up with 166,557.7596 is equal to v squared. And now finally, I want to do the last step, which is undo this square, do the opposite of square, which means take the square root of both sides. So I'm going to take the square root of this side and the square root of this side. This technically produces a positive and a negative, but, so square root. We know that speed can only be positive, right? Speed is a magnitude, it's a scalar, it's not a vector. So that final speed is the positive version. Final speed. We have 3 significant figures, so 408 meters per second. Think about it, that's very fast. That's how fast a plane goes when it takes off. Or sorry, an F-16 fighter jet. Okay, let's turn the page. The second type of mechanical energy is gravitational energy, gravitational potential energy. You'll go through and get this from the notes. Basically, gravitational potential energy depends on what you define as your reference point and your height of something. So for example, we have this image from the lesson. The pole has a certain amount of energy if I define the reference point as the guy's feet. However, if I define the reference point down here, well, now its height is very, very high, so it has even more energy. So it's all about your reference point. So let's go to this example. Daniel climbs the stairs to reach the second floor. So he goes from down here to up here. He has a mass of 63 kilograms, and he goes up a height of 12 meters when he goes from the first floor to the second floor. So if I want to find his gravitational energy, I'm going to use the formula mgh. His mass is 63, g is 9.8, and his height is 12. Notice these are not vectors, these are just scalars. I'm just using the numbers. My life is a lot easier because I don't have to worry about direction. And I'm going to multiply now 63 times 9.8 times 12. This is another case where, be careful, mass is always in kilograms. Multiply these 3 things together, and I get 7,408.8 joules. So therefore, the gravitational potential energy is 7.4 times 10 to the 3 joules. There you go. And just a reminder, well, you're going to get this at the end, your mechanical energy that something has is the addition, the sum of your gravitational potential energy and your kinetic energy. Okay, hope this was an enjoyable lesson, and until next time.